Welcome to Brain Vision.
Hi, in the given problem, there is a thin, uniform rod with a negligible mass, which is attached with a spring to a hinge point P, as shown here in the figure. This is the rod. One of its end is fixed here at the point P, and its another end is attached with a spring. This point P is frictionless, and there is a uniform magnetic field which is coming out perpendicular, which is getting in to the plane of paper perpendicularly. The magnitude of this magnetic field is given as 0.340 Tesla. There is a current passing through this rod in downward direction whose value is given as I is equal to 6.50 ampere. The total length of this rod is given as L is equal to 0.200 meter. The spring factor for this spring, the given spring, is K is equal to 4.80 Newton per meter. Now, in the presence of electric current passing through this rod and the magnetic field, this rod will start experiencing a magnetic force in the direction as shown here. And this force, the expression for this force is given as F is equal to B into I into L. And using Fleming's left-hand rule, the direction of this force is as shown in the figure. Now, in the first part of the problem, we have to find the torque due to this magnetic force on the rod. So, to find this torque, we assume this force to be acting at the center of mass of the rod. If the force is assumed to be acting at the center of mass of the rod as shown in the figure, then the torque acting on this rod will be given by tau is equal to the value of this force, which is F, multiplied by the perpendicular distance of this force from the point of rotation, means P, and that is equal to half of the length. So we can say it becomes BIL multiplied by L by 2, or simply PIL square by 2. So when we plug in all the known values for magnetic field, this is 0.340 Tesla multiplied by the current, which is 6.50 ampere, the length, the square of 0.200, and divided by 2, that is in meter. So finally, this answer for the torque acting on this rod comes out to be tau is equal to 0.044 Newton into meter, which becomes the answer for the first part of the problem. Now, in the same part of this problem, we have to discuss this force. It is correct to take this torque assuming the force to be acting at the center of mass. Suppose we do not assume the force to be acting at the center of mass. In that case, the force will be supposed to be acting on the rod uniformly over whole of the length. So we consider first of all the point P, and then suppose the opposite end of the rod is Q. Hence, the same force will be acting at both the points, means the force acting at point P, Fp, is equal to BIL. Similarly, F at Q is also BIL. But when we will find the torque, at a point acting at a point P, the perpendicular distance of P from the point of rotation is 0. So the torque will come out to be 0. And when we find a torque about taking the force at this point Q about a point P, then this torque comes out to be the force Fq multiplied by whole of the length, means it becomes BIL squared. So on an average, the torque will become torque acting at P plus torque acting at Q divided by 2, or we can say this is 0 plus BIL square by 2, or we can say this is BIL square by 2. Hence, the expression is same as when we have considered the torque to be the force to be acting at the center of mass. Hence, the assumption is correct. Now, in the second part of the problem, we have to find the total energy stored in the spring. So, now, in the second part of the problem, first of all, before finding the energy stored in this spring, first of all, we have to find whether this spring is stretched or compressed. So, as the direction of this magnetic force acting on the rod is away from the wall, this is the wall, so obviously the spring is stretched when it is in equilibrium. So we can write as the direction of magnetic force acting on the rod is away from the wall. So the spring is stretched. Now we have to find the energy stored, elastic potential energy stored in this stretched spring, for which we will find the extension in the spring and let it be the extension. So to find this extension, which we can say as delta x, the angle which this rod is making with the horizontal is given as 53.0 degree. And here PQ is the length of this rod. So in order to find this delta x, taking the component of the length of the rod along the horizontal, it comes out to be L cos 53.0 degree, and similar will be the value of extension in the spring. So we can say extension in the spring is L cos 53.0 degree. Hence, the elastic potential energy stored in the stretched spring is given as half K, the square of delta x, or we can say half into K, which is 4.80 Newton per meter multiplied by delta x, which is L cos 53, the square of 53. So plugging in all these values here, the value of this elastic potential energy comes out to be 0.0347 joules, or we can say this U is equal to 34.7 millijoules, and it becomes the answer for the third part of the problem. Thank you.